covalent bond and also dipole bond. Correct? Now the next heading are multiple covalent bonds. So far we have discussed about this. Multiple covalent bonds. With more than one electron pair, within the two combining atoms. Multiple covalent bonds are formed. For example, O2 molecule. So in O2 molecule, we take each oxygen with the 2s2, 2p4 configuration. The oxygen atom has two unpaired electrons. Same with another oxygen also. So when two oxygen atoms, they want to form a bond, each oxygen atom contributes this is Lewis dot structure. So 2, 4. 2 here, 4 here. Now each oxygen contributes 2 electrons for bonding. This oxygen also contributes 2 electrons for bonding. Total 4 electrons are contributed. These 4 electrons become 2 pairs, and these pairs are equally shared by both oxygens. So here how many pairs are shared between 2 oxygens? 2 pairs, that's right. A double covalent bond is formed. This is the first example for multiple covalent bonds. Oxygen forms a double covalent bond by sharing how many electron pairs? 2 pairs. Now to take the next example, I am going for the second example. What is your N2 molecule? So nitrogen has 2s2, 2p3 configuration. So 3 single electrons or unpaired electrons. Now another nitrogen, same case. 3 unpaired electrons. So when 2 nitrogen atoms are going to form a bond, here it is total 5 electrons, or you can say 2, 3, 2 here, 3 here, or overall 5 electrons, plus another nitrogen, which again 5 electrons. Now each nitrogen contribute 3 electrons per bond. So 3 plus 3, 6 electrons become 3 pairs. Now each nitrogen is held by a triple covalent bond. Because of this triple bond between 2 nitrogen atoms, God's creation, though nitrogen is present 78% in the atmosphere, it won't cause any harm to us. Though we are inhaling, exhaling, nitrogen is abundant around us. But it is not causing any harm because 2 nitrogen atoms are connected by triple bond. To break this triple bond, high energy is required. High bond dissociation energy. High bond dissociation energy. Or 225 kilocalorie per mole. So what are the 2 major components of the Earth atmosphere? N2 and O2. N2 is present 78% by volume. O2 is present 21% by volume. So these 2 constitute 99%. The remaining 1%, other gases like CO2, released by plants. What? CO2? Released by plants, yes. Nighttime CO plants release CO2. During sunlight, daytime, they take CO2 and do photosynthesis. Nighttime they release CO2. That's why we are advised not to sleep on the trees during night time. Because CO2 is 1.5 times heavier than air. When you sleep in under a tree during night time, whatever the CO2 released, it falls on you. You are inhaling only CO2. You will become severe headache, you become vomiting sensation, you will become drowsy, many symptoms arise. That's why this is a medical entrance exam question this month. People are advised not to sleep under trees because option 1, some devils and ghosts will stay on the trees during night time. Option 2, some birds will excrete on you. Option 3, they release oxygen during night time. Option 4, they release carbon dioxide in the night time. So last option is correct. Because CO2, though it is not poisonous, gas, people die in the atmosphere of CO2 because of lack of oxygen. That's why you go to Death Valley in Java Islands. Due to volcanic activity, so much of CO2 is released. CO2 don't go up, it will always come down because it is only times heavier than air, 1.5 times. So the entire valley is filled with CO2. If any animal or human being enters into the valley, first he suffocates, he feels breathlessness, he takes deep breaths, but no oxygen. Within few minutes he will die. The same case, if any unused wells are there in your locality, the well is not used for a long time, whatever the CO2 is there, it will go and accumulate there. So people don't know, they call some laborers to clean the well. They go down. First one person will go, he feels suffocated, he will cry for help. The second person will go, third person will go, all the way there. So CO2 is, though it is not poisonous, why we die in the atmosphere of CO2? Because of lack of oxygen. So, CO2, carbon monoxide, a mixture of inert gases, other pollutant gases like sulfur dioxide, like methane, all these constitute only 1%. Major constituents are N2 and O2. Suppose if God curses us, these human beings are highly cunning and they are cheating nature. If he curses, my dear oxygen and my dear nitrogen, they are in very large proportion by volume. If God curses to react both of these, N2 and O2 become NO, nitric oxide. So generally they don't react in the atmosphere. If God curses, they react, we all die within few minutes. Why they don't react among themselves in the atmosphere? While nitrogen and oxygen, though they are present in larger proportion, why they are not reacting with each other? Because to react each other, you have to break this triple bond. You have to break this double bond, which require a temperature more than 3000 degrees centigrade. So what is the temperature required to react N2 and O2 to form 2NO? A temperature of more than 3000 degrees centigrade. The highest temperatures recorded on the planet Earth is in the Californian desert. This year it is almost 55.6 degrees like that. That is the highest temperatures on the planet Earth. So you can't produce 3000 degrees centigrade. That's why N2 and O2 do not react in the atmosphere. Write the assertion labeling type question. Assertion: N2 is inert in atmosphere. N2 is inert in atmosphere. Reason: due to the presence of half-filled orbitals and stable configuration. Due to the presence of half-filled p orbitals and stable configuration. If this question is asked, what is your answer? SH is true, reason is false. A is true, R is false. Why R is false? Because we are not considering nitrogen atom to have half-filled orbitals. We are considering nitrogen molecule. In molecule there are no half-filled orbitals. So write the one more point. N2 is enough in atmosphere due to its high bond dissociation energy. N2 is inert in atmosphere due to its high bond dissociation energy. Next relevant point. Which of the following is an endothermic change? Which of the following is an endothermic change? Option 4. Now the first option, 1 and 2. Second option, 1 and 3. Third option, 1 and 4. Fourth option, 2 and 3. Yes, anyone? Option D, fourth option. Option 3. So he is right. We have first option just now we discussed. N2 and O2 do not react. Why? Whenever they want to react, you have to break a triple bond between two nitrogen atoms and you have to break a double bond. Both require huge energy to break their bonds. It is a highly endothermic reaction. What is the next one? Na plus N molecules of water. Na plus is surrounded by N molecules of water. It is called hydration. Hydration is always exothermic. That second option is right. It is hydration and it is always exothermic. That second option, we write that it is hydration and it is always exothermic. Delta H is equal to negative. What is the third option? It is electron gain enthalpy. When an electron is added to an atom, it becomes a negative ion and release energy. So third option is electron gain enthalpy. It is called EA1, first electron gain enthalpy. Actually electron gain enthalpy You can also show like this. Delta Eg H1 is always negative, exothermic. Here, H2 to break the bond, then only to convert into H. So here energy is required. It is bond dissociation. Bond dissociation. Always endothermic. This is also always endothermic. Delta H is equal to plus 44 kilocalorie per mole. So for how many delta H is positive? The first one and last one. Whenever delta H is positive, it is called endothermic. Whenever delta H is negative, it is called exothermic. Then you may ask me, will under any condition N2 and O2 of the Earth atmosphere react or not? Obviously the answer is yes. They react during heavy lightning and thunder. When monsoon clouds, your Meghalaya is famous for clouds. Clouds are highly charged. Whenever two electrically charged clouds they interact, a big lightning comes due to electric discharge. And this lightning produces temperatures more than 3000 degrees centigrade. So during lightning and thunder, N2 and O2 of the atmosphere react to form NO. That NO again reacts with atmospheric oxygen to form NO2. That NO2 dissolves in rainwater to form nitrous and nitric acids. These acids come along with the rain and fall on the earth. They react with the salts of the earth and form nitrates. Plants require soil nitrates to flourish or to give good yields. Plants directly cannot utilize the atmospheric nitrogen. So how do plants receive nitrogen? Through soil. Through air they can't take. Scientists are trying to develop plants which can directly use atmospheric nitrogen, but they fail so far. If anybody do that, it is a miracle for the world. You all can also try in your future. Why is it a miracle for the entire globe? Because plants, whether you do fertilizers or not, directly they take atmospheric nitrogen and give bumper yields of the food products. You can eliminate the hunger, misery from any corner of the planet. Everywhere food grains are there. Everywhere fruits are there. Everywhere vegetables are there. In rich abundance. So, but soil is poor in nutrients. Just say every year what we had? Fertilizers, minerals, many things are added to the soil to enrich the soil with nitrates, phosphates and all. Of course, intermittently, as you are bad students, you also study in between the two crops. You also grow some leguminous plants like Arachis hypogea. What is Arachis hypogea? Groundnut. Groundnut, the leguminous plant. This groundnut plant has root nodules in which rhizobium bacteria is there. When you pull the groundnut plant from the soil, these rhizobium root nodules remain in the earth. Soil is enriched with nitrates. Because these rhizobium bacteria fix nitrogen in the soil. That's why you should not grow rice, crop, again rice, again rice, again wheat, no. What the agricultural scientists do, they advise between one rice crop, one wheat crop, in between you have to use a leguminous crop. Your soil will be automatically enriched with nitrates. So actually, the entire hunger on the planet is almost eliminated by one plant scientist who got Nobel Prize, who developed many disease-resistant varieties of the hybrid seeds, who received the Nobel Prize. Who is he? Nobel Prize is called father of green revolution in the entire world, not father of Indian green revolution. Father of green revolution for the entire world. The answer is Norman Borlaug. Norman Borlaug is an American who wanted to study agricultural science, but his graduation marks are very low. Thus he could not get a seat in agricultural science. Instead he got a seat in forestry. So he studied forestry as a course and got a government posting and working as an employee in a forest. Where some tribal people, they grow in forest areas, tribes to be there. I think Meghalaya is also full of tribal people. Hope they know. So these tribal people, they grow certain crops. And Norman Borlaug was posted there. He identified what they are doing. He is observing. After so much of observation, he did some cross-pollinations and produced good quality seeds which will do more yield of the products, plant products, which are disease resistant. And luckily, at the time of independence, he also visited India. He gave many varieties of, hybrid varieties of rice, paddy to Indian farmers, the farmers of Bangladesh, Pakistan. At the time, Pakistan and Bangladesh are together. So most of the South Asian countries were benefited by the hybrid seeds given by Norman Borlaug. And he was awarded Nobel Prize for peace, because there is no Nobel Prize for agriculture or plant sciences. So that's how you may also get a Nobel Prize if you develop a plant that directly utilize atmospheric nitrogen. Okay, try. Who knows? Oxygen configuration. 2s2, 2, 3, 4. Now carbon and oxygen, let us say they are talking to each other. Carbon says, my dear oxygen, I have 2 unpaired electrons. And oxygen replies, I do have 2 unpaired electrons. Then you shall do one thing. Your 2 unpaired electrons, my 2 unpaired electrons, we can pair of them and form a double covalent bond. So in carbon monoxide, initially when they talk to each other, the two unpaired electrons of carbon, the two unpaired electrons of oxygen, they pair up and form a double covalent bond. C double bond group. Now after this, immediately oxygen looks at carbon. It has one vacant orbital. Carbon has what? One vacant orbital. Oxygen has how many lone pairs? 2 lone pairs. So why can't I donate one more lone pair to the vacant orbital? It immediately proposes to oxygen. Oxygen, I'm going to do one more thing. It is going to talk to carbon. Oxygen says, my dear carbon, we are having one vacant orbital. Why can't I donate my one extra lone pair to you? So that we will get 3 bonds. More the number of bonds formed between 2 atoms, more the stability. Then immediately carbon agrees. Okay, you do that so that one more bond is formed. Now this is a triple bond is formed. Two are normal covalent bonds. One is a coordinate covalent bond. Two are normal covalent bonds by sharing of electron pairs. What is the third one? Coordinate covalent bond is always formed if one is the donor, the other is acceptor. Here who is the donor? Oxygen is the donor. Who is the acceptor? Carbon is the acceptor. An arrow is indicated by coordinate covalent bond. That arrow represents coordinate covalent bond, which is from donor to acceptor. From donor to acceptor. Now, other than arrow, you can also show it's a normal triple covalent bond, but donor gets plus, acceptor gets minus. So when I discuss the structure of carbon monoxide, I would like to add 3-4 points more, which you are going to study in your coordination compounds. So write that point. CO, carbon monoxide, is one of the strongest ligands. Is one of the strongest ligands. From here. Carbon monoxide is one of the strongest ligands. So one day he asked me a doubt, how to know which is strong ligand, which is weak ligand. So immediately I asked him to see the spectrochemical series in your NCERT textbook. There are some halide ions, water. These are weak ligands. Ammonia, ethylene diamine, PDTA, they are moderately strong. So what are the strong ligands for the spectrochemical series? Carbon monoxide, cyanide, okay. Thiocyanate. Chemistry is moderately strong. NO. So why I called, he asked me to get anyhow, he is able to do the reply also. He studied and able to remember. So carbon monoxide is a very, very strong ligand because the carbon atom is carrying both a negative charge and lone pair. The carbon atom is carrying negative charge and lone pair and has strong ability to donate the lone pair. So here one point we have covered, which we are going to discuss in your coordination compounds. Here I am going to cover one more very important point. Carbon monoxide is called a pi-acid ligand. Carbon monoxide is also called a pi-acid ligand. Nickel solid plus 4CO gas, NiCO 4 times. This is called nickel carbonide. Nickel carbonide. Whenever metal and carbon monoxide react, the compounds are called metal carbonides. Here the oxidation state of metal is 0. So many students ask this also as a doubt, as in one of your mock tests, this question was there. In which of the following the metal has 0 oxidation state, or there is no change in oxidation state? So the answer is nickel carbonide. So nickel, atomic number 28, has this configuration. (3D8) 4s. The first row of D block elements, their configurations should be at your fingertips. Atomic number 21 to atomic number 30. Practice all the electronic configurations of those 10 elements. In the examination, the paper center won't give you. Now, By seeing this nickel, 4 carbon monoxide molecules, they approach nickel. How many? 4 of them. My dear nickel, you provide 4 vacant orbitals so that we donate. Each one of us will donate an electron pair and form 4 coordinate covalent bonds. Then nickel says, I am readily having 3 vacant orbitals. So donate. But we have 4. We are showing only 3 vacant orbitals. Then nickel says, don't worry, you are a strong ligand. I will pair my 2 s electrons with the electrons. So the s electrons change their position from here and go here and pair them. Then what is the reorganized configuration? 3d10, 4s0. Nickel has not lost any electrons. That's why its oxidation number remains 0 only. Now total how many vacant orbitals provided by nickel? 4. One is S, 3 are P. sp3 hybridization occurs. It is a tetrahedral complex. So nickel carbonide, a tetrahedral complex. With sp3 hybridization is formed. So in this complex, there is a bond between metal and carbon. Whenever there is a bond between metal and carbon, we call those compounds as organometallics. So nickel carbonide is an example of organometallic compound. What is nickel carbonide? Since there is a metal carbon bond, it is called organometallic. Now write a question. Nickel carbonide is number 1, option 1, sigma bonded organometallic. Number 2, pi bonded organometallic. Number 3, both sigma and pi bonded organometallic. Both sigma and pi bonded organometallic. Last option, it is an ionic organometallic. Ionic organometallic. It is so important. Without knowing this question, same dialogue, you should not enter into exam hall. Even you don't accept your hall ticket also. So what is the answer? Option 1. Option 1. So Dr. Rocky's answer was called as a natural answer, which is wrong actually. Because Rocky has seen between nickel and carbon, there are sigma bonds. That's why naturally anyone, teacher can also say, sigma bond is formed here. Sigma bonded organometallic, the answer. But the answer is third option. It is both sigma bonded and pi bonded. Sigma and pi bonded organometallic. That's how I will explain. So when nickel forms the coordinate covalent bond with carbon monoxide, as Dr. Rocky has predicted, definitely it should be a sigma bonded organometal. But actually after this sigma bond formation, nickel has completely filled the orbitals, because two s electrons also came back and paired with the D8 and became deepen. This completely filled d orbital, it proposes to this carbon, my dear carbon, you have a vacant orbital called pi star anti-bonding orbital. In carbon monoxide, carbon has one vacant pi star. Donated one electron pair to me. I accept it. Now in return I want to give a gift to you. Return gift. I want to donate one electron pair to you. Then carbon says okay. Because more the number of bonds formed between two atoms, more the stability. So that's why one side sigma bond, the other side is lateral overlap, gives a pi bond. So nickel carbonyl is what type of metal carbonyl? It is both sigma bonded as well as pi bonded organometallic. It is both sigma bonded and pi bonded organometallic. You know, the electron pair donor is called Lewis base. Electron pair acceptor is called. So here carbon monoxide in the reverse direction, that bonding in the reverse direction, it is accepting an electron pair and forming a pi bond due to lateral overlap. That's why it is called a pi acid ligand. Why it is called the term ligand? It is donating an electron pair. That's why it is called a ligand. Since it is donating electron pair, it is called a ligand. And strong ligand, we already discussed. Then why the word pi acid as a prefix? Because after the formation of coordinate covalent bond, in return, it is accepting electron pair from the fulfilled d orbitals of the metal and forming a pi bond. That's why it is called a pi acid ligand. Very, very important. So whenever I say important, you please concentrate on those points. One more point. Some students are still inhibition what to study, what not to study. Each table is filled with so many books, piled up. Still some more books you can pile up. Two basic things. Classroom notes, NCERT textbook are the first two tools you require. So after finishing these two, then only you can go to any other book. Classroom notes is a ready reckoner. Because 2 days back, this doctor, what is his name? Shalom. City name. That's a Michael John. PH? Oh, very good. Sean. No, I'm not criticizing him. He brought it out. To describe an orbital, he did what left out to me. To describe an orbital, the number of quantum numbers required. Is it the same now? You remember or not? To describe an orbital, the number of quantum numbers required are 1, 2, 3, 4, 4 options are there. I said, no, you bring your notes. Your administration notes. And see the subheading quantum numbers. So within half page you will find the same point. To describe an orbital, the number of quantum numbers required are 3. He himself wrote in the notes, but he brought the same note to me. Not only he, Dr. Charge, or Charge. Not only he, many students are bringing. So please, you revise the notes, revise the textbook. So as the days are passing, you should consolidate yourself, chapter-wise consolidation. Finally, at a particular point of time, you should not going to lose any question from that chapter. You have to be equipped in that way. That is all in your hands. Of course, luckily you are also very good students. You are doing a focused work. Generally, in the study hours, we are doing a lot of efforts. So revise the classroom notes, revise the textbook, chapter-wise, repeatedly. So that is the thing. Okay? So carbon monoxide is a pi-acid reagent, and the type of organometallic is a sigma as well as pi-bonded organometallic. Grignard reagent is a sigma bonded organometallic. CH3MgBr, methyl magnesium bromide, is purely Grignard reagent. It is what kind of organometallic? Sigma bonded. Organo metallic. Disodium acetylide. This is also sigma bonded organometallic. It is both sigma and pi bonded. Organometallic. Then there are some compounds. This is the cyclopenta dienyl anion. What is this? Cyclopenta dienyl anion. Now in this, then this negative charge shifts, pi bond shifts, this pi bond shifts. There is a delocalization of resonance. So the entire thing is having negative charge, which we can show like this. Cyclopenta dienyl anion. Here I am writing another cyclopenta dienyl anion. Between these two cyclopenta dienyl anions, what are these? Cyclopenta penta, dienide anion. Between these two anions, if iron atoms are there, the vacant orbitals of iron receive this pi electron cloud and forms a bond. This is famously called ferrocene. Cyclopentadienide iron, we call it ferrocene. It is a pi bonded organometallic. Organometallic. So how many types of organometallics? 3 types. One is sigma bonded, one is purely pi bonded, one is both sigma and pi bonded. What are the examples of sigma and pi bonded organometallics? Not only nickel carbonate, all metal carbonides. Write a point, all metal carbonides. All metal carbonides within the brackets MiCO 4 times, comma FeCO 5 times, iron carbonate, CrCO 6 times. All metal carbonides in which metals have 0 oxidation state are examples of both sigma and pi bonded, organometallics. Both sigma and pi bonded organometallics. Write the next point. So multiple bonds, in multiple bonds, so the coordinate covalent bond or native bond, it is a special type of covalent bond. It is a special type of covalent bond. Which is formed by sharing of an electron pair which is contributed by only one of the binding atoms. Which is contributed by only one of the binding atoms to form coordinate covalent bond. To form the coordinate covalent bond, one of the binding atoms should have a lone pair of electrons. One of the binding atoms should have a lone pair of electrons. And the other should have a vacant orbital. And the other should have a vacant orbital. Examples. Number 1, ammonia with a lone pair plus boron trichloride with a vacant orbital. So this lone pair is donated to this. So you get ammonia, boron trichloride. Ammonia, boron trichloride. The second example, again I am taking ammonia. H plus, it donates electron pair. The former one is called ammonium ion. The third example, water plus H plus. You get H3O plus. Which is called hydronium ion. Number 4, nickel and carbon monoxide. Number 5. Similarly, iron with carbon monoxide. Which is a trigonal bigonal shape. Carbonate. Six carbon monoxides. Six coordinate covalent. Only carbon monoxide. Two normal covalent bonds, one coordinate covalent. All complex ions. Example, CuNH3, 4 times 2 plus. Tetramine copper 2 ion. Tetramine copper 2 ion. What is the spelling of amine? AMMINE. B. FeCN6, ferrocyanide ion. C. FeCN6 3 minus. Why it is ferricyanide? Ferrocyanide, ferricyanide. If it is +2, we call it ferrocyanide. If iron is in +3 state, it is called ferricyanide. Now 9. BF4 minus, which is called borofluoride ion. So BF3 accept an electron plane from F minus. BF4 minus. F6 3 minus. Many students ask this also as a doubt, as it is one of the questions in our mock test. When ALF3 react with KF, the complex formed is, or the soluble compound formed is K3AlF6. Hexafluoroaluminium 3 ion. Many students ask me this as well. Next, in hemoglobin, the oxygen forms, the O2 molecule forms. In hemoglobin, the O2 molecule forms a coordinate covalent bond with Fe2 plus. Now, we have studied so far different varieties of bonds. I have the covalent, again covalent, we divide into non-polar covalent, polar covalent, multiple bonds, like that. Next we completed coordinate covalent bonds. Now, before going to the next type of bond, that is metallic bond, here I am going to discuss 2-3 points. Properties of covalent compounds. Covalent compounds exist in all the 3 physical states. Covalent compounds are either liquids or gases or solids. For example, benzene is a liquid covalent compound. Water is a liquid covalent compound. Ammonia is a gaseous covalent compound. Methane is a gaseous covalent compound. Sugar is a covalent solid. Naphthalene is a covalent solid. Camphor is a covalent solid. So covalent compounds can exist in all the 3 physical states: liquid, gas, solid. Petrol, diesel, all these are liquid covalent compounds. Paraffin wax, the solid compound, covalent. And covalent reactions are slow when compared to ionic reactions. Why covalent reactions are slow? Because they involve in bond breaking and bond making. Since covalent reactions involve bond breaking and bond making. Bond breaking and bond making. They are relatively slow when compared to ionic reactions. Ionic reactions. Covalent bond is directional. Ionic bond is non-directional. That's why, since ionic bond is non-directional, ionic compounds do not exhibit it as. Very good. Stereo or space isomerism. While covalent compounds, if the bonds are directional, they can exhibit stereo or space isomerism. Now, just write the heading. Valence bond theory, VBT. Valence bond theory, VBT. Please you also write the heading valence bond theory, VBT. It explains the formation of covalent bond. It explains the formation of covalent bond in terms of orbital overlap. In terms of orbital overlap. Now earlier, listen to this point. Earlier we have studied the Lewis theory to explain the covalent bond formation just by sharing of electrons in the form of dots. So covalent bond can be explained by Lewis theory with the help of dot structures. The second theory is VBT, valence bond theory. The valence bond theory explains what the formation of covalent bond. How? By orbital overlap. In this there are certain points, just I read out, no need of noting down. They are all in the textbook, just listen to the points. A covalent bond is formed due to the overlap of two half-filled atomic orbitals. So what type of orbitals overlap to form a covalent bond? Half-filled means single electron orbitals overlap. During the process of overlap, the electrons get paired and energy is released, bond is established. That is the second point. The third point is strength of bond. The Lewis theory, with the help of dots, do not explain the strength of the bond, whereas VBT explains about strength of the bond. So strength of covalent bond is directly proportional to extent of orbital overlap. This point you can mention. Strength of covalent bond is directly proportional to the extent of orbital overlap. So greater the extent of orbital overlap, greater the strength of the bond. Here one more point. just listen to it. N to N overlap or axial overlap. Give sigma bond. N to N, one orbital N, another orbital N. N to N orbital overlap gives sigma bond. It is also called axial overlap. Sidewise overlap or lateral overlap gives pi bond. So VBT explains about sigma and pi bonds. Sigma bond is formed by axial or N to N overlap. Pi bond is formed by sidewise or lateral overlap. Okay? Next. Between sigma and pi bond, sigma bond is always stronger than pi bond. And between sigma and pi bond, sigma bonds only explain the shape of the molecule. Pi bonds never. So these are the points in the VBT, valence bond theory. Based on VBT, write this point. Based on VBT, the decreasing order of the strength of different bonds, sigma Pp is greater than sigma Sp is greater than pi P. But vegetable molecule has the highest single bond energy. Highest single bond energy in the periodic table. Within brackets 104.5 kilocalorie per mole in the periodic table. Thus, 1s orbital overlap occurs to the maximum extent. Orbital overlap occurs to the maximum extent. So actually here, what is this? How to remove this? Valence bond theory. The covalent bond is formed by overlapping of atomic orbitals. Half-filled orbitals contain electronic parallel spins. Overlapping of orbitals cause delocalization of electrons, which lowers energy. Strength of covalent bond depends on extent of orbital overlapping. For example, axial overlapping gives sigma bond. So 7 point the bond formed by axial overlapping sigma. 8 point the bond formed by sidewise pi bond. Sigma 1 is always stronger than pi bond due to greater extent of orbital overlap. So these orders also we have given. Pi pp less than less than sigma ss less than sigma ss sp. I think this segment is missing. This also includes diode sigma pt greater than sigma sp greater than this I didn't write, but we have sigma ss 5 pp is the last. But why I didn't write sigma ss? Because 1s orbital over that is the strongest in the periodic table. So this is 1s orbital over. It is the strongest bond. Strongest single covalent bond. This is sigma pp. So we are want free rotations possible. Free rotation about a pi bond is not possible. This point is also important. This we already discussed. Shape of the molecule, not. Only 3 points are important in this. After writing these 3 points, we have one more point. Write one more point. Sigma bonded electron cloud. Sigma bonded electron cloud is cylindrically symmetrical. Sigma bonding electron cloud is cylindrically symmetrical about the internuclear axis. About the internuclear axis. What do I write this? Sigma bonded electron cloud. Like a cylinder, symmetrical around the internuclear axis. Next point, 5 bonded electron cloud. Five bonded electron cloud forms 2 electron cloud regions. Forms 2 electron cloud regions. Above and below bonded electron cloud or bi-bonded electron cloud forms two electron cloud regions above and below the internuclear axis. Internuclear axis. Because these two upper lobes, they overlap one electron cloud region. The lower lobes, when they overlap, one more electron cloud region. So how many electron cloud regions are there? Two electron cloud regions, one above, one below the internuclear axis. Based on this, write on JEE question. Previous JEE question. Of course, NEET level only. The number of electron cloud regions above and below the internuclear axis in ethyl molecule in ethyl molecule. Option 1, 2. Option 2, 4. Option 3, 1. Option 4, 6. Yes, anyone? Number of electron cloud regions above and below the internuclear axis in ethyl molecule. Ethyl means C2H. It is ethyl. Ethyl means a triple bond. Triple bond always consists of 1 sigma, 2 pi bonds. Triple bond always consists of 1 sigma, 2 pi. When 2 pi bonds are formed between 2 carbon atoms, means 2 p orbitals on each carbon should have a lateral overlap. Now this orbital in this axis will be overlapping. And these orbitals also overlap. Or in a more space place is about. So in ethyl, triple bond, one is sigma bond, all the 2 pi bonds are formed. These are p orbitals on this axis overlap. Again, one more set of p orbitals are there. is also over. So, above and below the internal axis, because of this orbital overlap, one electron clouding. This orbital overlap, similarly below also. So in the ethyl molecule, how many regions of electron cloud are present above and below the internal axis? 4. 2 pi bonds means 2 upper lobes, 2 lower lobes. Again, one more 2 p orbitals, one more overlap. So totally you have 4 regions of electron cloud. A very simple point. The professors of IITs framed this, and students are clean bowl. Most of them could not make it. Because this is fundamental, they miss. So these are our valence bond theory, coordinate covalent bond. Write the next heading, metallic bond. Metallic bond. You all know metals are very hard with high melting points. Their strength is also very high. That's why you have metal grill for your windows. You have metal framed chairs you are sitting. Your metal frame for your wooden tables. So metals are very strong. Means the atoms are very strongly held. So how similar metal atoms are that much closely packed to give rigid structures? What type of attractive force is binding the metal atoms? That is metallic bond. So write the definition of metallic bond. Metallic bond is a strong electrostatic force of attraction metallic bond is a strong electrostatic force of attraction between a sea of electrons and positively charged metal ions called kernels. So what is metallic bond? It is a strong electrostatic force of attraction. Between whom and whom? Between a sea of electrons and positively charged metal ions called kernels. So I will explain this. When metal atoms are closely packed, this type of close packing in a three-dimensional pattern is called what? Very crystal lattice or space lattice. This is called crystal lattice. Or space lattice. Now, immediately student objects how similar metal atoms in which each atom has some electrons around it. Will the electrons won't deepen negative repulsions because they are that much closely packed. There must be tremendous repulsions between the electrons of one atom and the electrons of the other atom. Like that all neighboring atoms should repel with each other. In spite of these repulsions, still metal atoms are closely packed. So what is the reason for it? That we explain in the form of metallic bond. So in the formation of metallic bond, what the metal atoms do? They lose their valency electrons. What are their outermost electrons? They lose. When they lose the electrons, they become positive ions. Let us say each atom is losing one electron. Then each atom becomes one positive ion. Similarly, this also gives one more layer of electrons. Like this also. Every atom, metal atom, in the crystal lattice, they lose electrons and become positive ions. What these positive ions are called? Kernels. When they become positive ions, again positive repulsion must be there. Again electron repulsion. Now each metal atom, depending on the number of valence electrons, suppose if they are alkali metals, they can only lose one electron and become unipositive ions. If they are alkaline earth metals, each atom lose two electrons and they become bipositive ions or dipositive ions. It all depends on the number of valence electrons. But metal atoms lose electrons. Which electrons? The outermost electrons. And they become positive ions. And what are the electrons they lost?